Ever wondered how algorithms work in C programming? Today, we're going to unravel this mystery. Algorithms, in essence, are the heart and soul of programming. They are the step-by-step instructions that tell a computer exactly what to do and how to do it. Just as a cook follows a recipe, a computer follows an algorithm. In the grand scheme of programming, algorithms are pivotal. They're the foundation upon which all software, apps, and digital systems are built. But what makes a good algorithm? How do we design one? And why is algorithm design so crucial in C programming? These are the questions we'll be addressing in this video. We'll explore the fundamentals of algorithms, discuss their key characteristics, and walk you through the basic algorithm development process. We'll also shed light on the significant role algorithms play in computer science. So buckle up as we dive into the fascinating world of algorithm design in C. First off, what exactly are algorithms? This is a question that often puzzles many. In the simplest terms, algorithms are a set of instructions or a step-by-step guide to solving a problem or accomplishing a task. They are like a recipe that your computer follows to churn out a specific outcome. But how do they function in C programming, you may ask? Well, in C, an algorithm is a sequence of well-defined steps that takes some values, or a set of values, as input and produces some values or a set of values as output. It's like a function machine. You input something, the machine processes it according to its internal instructions, and then it gives you an output. Now let's take an everyday example. Imagine you're cooking a dish. You have a recipe, which is essentially an algorithm. It tells you the exact steps to follow, the ingredients to use, and in what order to add them. That's exactly how an algorithm works in C programming. It is a recipe for your computer, guiding it on how to execute a task efficiently and effectively. It's important to note that an algorithm is not the actual code, but the idea behind the code. It's a conceptual representation of how a particular problem can be solved. The same algorithm can be implemented in different programming languages, just like a recipe can be followed using different kitchen tools and techniques. So, why are algorithms so important? They provide a plan for solving problems. By having a clear plan, you can write efficient code that not only solves the problem, but also does so in an optimized way. In essence, algorithms are the backbone of any programming language, not just C. They are the foundational building blocks that guide computers in making complex calculations and carrying out numerous tasks. They are indeed the very heart of computer science. Now that we know what algorithms are, let's explore why their design is so crucial. At the heart of every piece of software, there is an algorithm. But why does the design of this algorithm matter so much? The answer lies in three key areas: efficiency, time complexity, and space complexity. First, let's talk about efficiency. A well-designed algorithm can perform tasks faster and with less computational resources than a poorly designed one. This is critical because it ultimately determines how responsive a piece of software will be. Imagine a web search engine that takes minutes to return results because of a poorly designed search algorithm. It wouldn't be a very popular choice, would it? Next, we have time complexity. This is a measure of the amount of time an algorithm takes to run, as a function of the size of the input to the program. It's important because it helps us understand how our algorithm's performance will scale as the size of the input increases. A well-designed algorithm should have a time complexity that grows as slowly as possible, allowing it to handle larger inputs without a significant increase in execution time. Finally, there's space complexity, which measures the total amount of memory that an algorithm needs. Just like time complexity, a good algorithm should have a space complexity that grows as slowly as possible. This allows it to handle larger inputs without consuming too much memory. In essence, the design of an algorithm directly impacts how quickly a program runs and how much memory it uses. This is especially important in today's world where we are dealing with massive amounts of data. A poorly designed algorithm could take days to run on large datasets, consume all available memory, and eventually crash. On the other hand, a well-designed algorithm could process the same data in a fraction of the time using minimal memory. So, whether you're designing a simple mobile app or a complex data analysis platform, remember that your algorithm design will directly impact the performance of your software. Clearly, algorithm design is an important aspect in programming that can't be overlooked. So what makes a good algorithm stand out? Firstly, clarity. An algorithm must be clear and unambiguous. Each step in an algorithm should be clear in its intent and must lead towards the solution of the problem. It should not contain any instructions that are unnecessary or confusing. Next, we have efficiency. An efficient algorithm is one that uses the least amount of computational resources, including time and memory. The faster an algorithm can solve a problem or the less memory it uses, the more efficient it is considered to be. Then comes robustness. A robust algorithm is one that can handle unexpected inputs or situations without crashing or producing incorrect results. It should be able to handle a wide range of inputs, even those that might not be anticipated when the algorithm is designed. Additionally, a good algorithm is generally simple and easy to understand. While complex algorithms can sometimes solve problems more efficiently, they are often harder to understand and debug, which can lead to errors and inefficiencies in the long run. Also, a good algorithm should be flexible and adaptable. This means it should be easy to modify or extend to handle new situations or requirements. This characteristic can save a lot of time and effort in the long run, as the algorithm can be reused in different situations. Finally, a good algorithm will produce the correct results. This might seem obvious, but it's important to remember that a fast, efficient algorithm that produces the wrong results is not a good algorithm at all. Good algorithms are those that are efficient, clear, and robust, among other traits. Algorithms aren't just important in programming, they play a significant role in the broader field of computer science. Let's start with data structures. Data structures are the building blocks of computer science, and they're all about organization. Algorithms come into play here by determining how these structures are accessed, manipulated, and managed. Whether it's a simple array or a complex binary tree, algorithms provide the instructions that make these structures work. Moving on to operating systems, algorithms are integral in managing resources efficiently. For example, scheduling algorithms determine the order of tasks, ensuring that your computer runs smoothly and efficiently. Whether it's deciding which application gets access to the CPU first or how memory is allocated, algorithms are making those decisions. Let's not forget about artificial intelligence. AI is fundamentally about creating machines that can think and learn, and algorithms are the backbone of this process. Machine learning algorithms, for example, allow computers to learn from data, make predictions, and improve over time. They're the reason why your social media feed seems to know you so well, or why self-driving cars are becoming a reality. So you see, algorithms are much more than a set of instructions for solving a problem. They're the gears that make the vast machinery of computer science run. They provide structure, manage resources, and even enable machines to mimic human intelligence. Indeed, algorithms are at the heart of computer science. Now, let's walk through the basic process of developing an algorithm. First off, we begin with the problem definition. It's crucial to understand the problem you're trying to solve thoroughly. Look at it from all angles, break it down into smaller parts if needed, and understand the inputs and expected outputs. Remember, a clear problem definition is the foundation of a strong algorithm. Next up is the designing phase. Here we lay out the roadmap for solving the problem. You might want to use flowcharts or pseudocode to visualize the logic and flow of your algorithm. This step is all about planning. Think of it as a blueprint for your algorithm, helping you to navigate through the coding phase effectively. Once we have a well-thought-out design, we move on to the coding phase. This is where we translate our design into C code. The key here is to focus on implementing the logic of the algorithm rather than getting bogged down in syntax. Of course, syntax is important, but our primary goal here is to ensure the algorithm works as intended. After coding our algorithm, it's time for testing. We run the algorithm with different input sets to verify its correctness. The testing phase is crucial as it helps to identify any errors or inefficiencies in the algorithm. If any issues are found, we loop back to the design or coding phases, make the necessary adjustments, and then test again. Finally, once we're confident that our algorithm is functioning as intended, we can consider it complete. But remember, the development of an algorithm doesn't truly end here. As we gain more knowledge and experience, we might find ways to improve our algorithm, making it more efficient or adaptable. And that's a brief overview of the algorithm development process. So, what have we learned today? We've journeyed through the world of algorithms, starting from understanding what they are to grasping their importance in our digital lives. We've delved into what makes an algorithm good and how they play a pivotal role in computer science. Lastly, we've navigated through the basic steps involved in algorithm development. If you're eager to further your understanding, consider diving into more complex algorithms, exploring various design techniques, or even starting your own algorithm project. Remember, the best way to learn is by doing. Keep practicing, keep learning, and you'll soon master the art of algorithm design in C. Until next time, happy coding.